we shall next discuss how to convert a deterministic finite automaton to an equivalent regular expression. Let's consider this language. L is equal to a power n b power m, where n comma m greater than or equal to 1. Means the corresponding automaton is precisely this. We read at least one A followed by sequence of A's, at least one B followed by sequence of B's. Since this being deterministic finite automaton, when we read a B here, we go to a dead state. When we read A here, we go to a dead state. On this, if we read AB, we continue to stay here. Now, regular expression corresponding to this, if you look at any string over here, base string is AB, or it is A followed by sequence of A's, B followed by sequence of B's. So 0 or more A's, 0 or more B's. So now we see that A star will give you 0 or more A's, B followed by B star will give us 0 or more B's. Now for this example, just by looking at this, one can extract the language as well as regular expression, but it may not be that easy for all deterministic finite automatons. So we look for an algorithm, a procedure, a systematic way of constructing regular expression out of a deterministic finite automaton. So the way we are going to proceed is like this. When I am at Q0, what part of string or what regular expression one can generate with respect to Q0? For example, when I am in Q1, what regular expression one can generate? For example, at Q1 you can see that it is A star. So in some sense, given a language, given a string from this language, we look at what substring can be generated until Q1. And like that, for each state, we analyze what regular expression at each state one can accept. And we use that information, and finally when we go to the final state, we analyze what is the regular expression at this state. That would be our final answer. So to obtain regular expression at Q2, that's precisely the regular expression for this deterministic finite automaton, we make use of regular expression at each state, or rather what part of string one can see at each of this state, that information will be used, carry forward until the final state. Using all this, we calculate the regular expression at Q2. Okay, so which means we are going to construct a system of equations. With respect to Q0, here is our equation. Since Q0 being the start state, we write epsilon for that. We just talk about the incoming arrows. With respect to Q0, there are no incoming arrows. So since this being the start state, we write epsilon. For Q1, you see that there is an arrow from Q0. So it is Q0 A, always state followed by the symbol. Then it is Q1 A. So it is always state followed by a symbol. Why are we writing epsilon? Because Q0 is the start state. Now, if you look at Q2, Q2 gets an arrow from Q1 and also an arrow from Q2 itself. D is also a state. With respect to D, it is Q naught B plus Q2 A plus dA plus dB. Okay. Although the regular expression accepted at this state may not be of use because it's a dead state, but just for consistency purpose, I am writing all of them. Okay, so one can simply use these three and solve. This is not required, but just to give you clarity on how equations are written, I am writing for this status. Okay. Now we start simplifying this. What we do, we know answer for this, substitute here and start simplifying this. So this becomes Q1 equals Q1A plus Q0 A. Q0 A is epsilon times A, which means Q1 is equal to Q1A plus A. So there is a theorem by Arden's. So Arden's theorem says you look at this expression as something like say R, this is also R, this one is P, this one is Q. So R represents the state, P is some expression, Q is some sub expression. If this is the case, then it says if R is equal to Rp plus Q, then R is P star Q. Okay. So in this case, so R is QP star. R is QP star. We will see the proof of this through after discussing a couple of examples. So which means this says you use this theorem here, you get Q1 is equal to A times A star. So what it says is at Q1 the regular expression is A star, which you can cross verify. Look at this. If you look at this starting from here, you can read A and continue to read A, so which means you get A star at Q1. Now use this value to solve for Q2, and Q2 says it is Q2B plus Q1B. Q1B is A star B. Again use this theorem, R is equal to Rp followed by Q. Q is some expression. Now solution says Q2 is A star followed by B followed by P star, which is this. So that's all. This gives you that at Q2 what we see is precisely this. Now this can be substituted here. At D what do we get? We get B plus A star BB star A followed by A plus B times D. Okay, now you can see this as R, the entire part as Q, and this one is P, this one is R. Now we get to see that solution is QP star, which means it is B plus AA star BB star A times A plus B the whole star. Now look at D. You get arrow from this, so it is B, or you come via this. At this stage you must have seen AA star BB star followed by A. Then after you reach, you can read any number of A's and B's, which is why we get A plus B star. Okay. So now what is that we have done using Arden's theorem and using this system of equations? Starting from Q naught, at each state what regular expression one can read, accept. So we developed a system of equations, and the way we have written is like this. For the start state it is epsilon plus, in case there are incoming arrows, that part should be written. For Q1 we focus only on incoming arrows, so you write state followed by the symbol, state followed by the symbol. Now start simplifying it. So this is straightforward. So this can be used here to get Q1. Value of Q1 can be used here to get Q2. So to simplify, we have used this theorem. The proof of this we shall see soon. And now this says when you have an equation like R equals RP plus Q, Q is some expression, P is some expression, R represents the state. Then solution to this is R equals QP star. Now if you employ that theorem over here, we get to see that Q1 is AA star and Q2 is this. And the output or the answer to this language or question is precisely this. The regular expression that you see at this state is precisely the answer to this automaton. Fine. Let's look at a couple of more examples. Consider this automaton. When we read a B, we stay at Q naught. On reading A, we go to Q1. On reading another A, we come over here. And we continue to read PC. And with respect to each state, transition on AB, both are defined. Now let's analyze the regular expression for this. If we follow our procedure, it says Q naught equals epsilon plus, we should write the incoming arrows, state followed by the input symbol. Similarly, Q1 followed by A. Now with respect to Q1, you see that Q1B plus there is an incoming arrow from Q naught, which is Q naught A. Fine. So now this is precisely what we are. What we do, we look at this. When we look at this, it is Q1 equals Q1B plus Q naught A. This can be seen as R equals RP plus Q. And Arden's theorem says if R equals RP plus Q, then it is QP star. Fine. So which means if you employ this rule, what we get is Q naught A times B star. So if you look at Q1, what do we get? We get Q naught A followed by B star. And let's employ this here. Substitute the first equation. We get epsilon plus Q naught B plus, in place of Q1 substitute Q naught A B star followed by A. This can be simplified to epsilon B plus A B star A times Q naught. Now this is R, this is Q, this is R, and this one is P. Now solution says Q naught is B plus AB star A to this star. Before that it is epsilon, so epsilon into this. So then what we get is precisely B plus AB star A the whole star. Now let's look at this. So the regular expression corresponding to this is precisely this. What? Because Q naught is the accept state. So B plus AB star A whole star. If this takes 0, then it accepts epsilon. If you take the first component, then it accepts so many B's. It is true. Or you can read so many B's followed by A, B star, and come back on A. And this can be repeated. Correct? Which means you get to see that zero number of A's, or whenever it reads A, it always reads even number of times. So which means the language accepted by this is precisely even number of A's. It may contain just B's, yes, or it may contain B followed by A, followed by B, followed by A, and followed by B. So prefix and suffix can be B star, that is given by this. The moment you read A, you may read B star followed by another A, that is given by this. Now it's so nice that a procedure like this gives you a regular expression, and in a systematic way we have built, or we have developed the recurrence, we have developed the regular expression, and in some sense it is recursively defined, which is why we call it as recurrence relation and so on. Something like Q1 is defined in terms of Q1, Q naught is defined in terms of Q naught. Okay, but if you carefully observe, because we need solution to Q naught, we try simplifying Q1 first and then substitute here, so that we obtain solution to Q naught. So the order of simplification matters, so that depends on the question. So one has to see in what order one should proceed, so that we get solution to the equation Q naught. Now this was the point. Some of the questions may be little tricky. For that, a procedure like this shall definitely help us in obtaining regular expression. So let's look at a couple of more case studies, and slowly we will get into the intuition behind this theorem, and why a procedure like this will always work. And instead of looking at the incoming arrows, can I look at outgoing arrows? Can I look at from Q naught? Can I look at outgoing arrows? From Q1, can I look at outgoing arrows? If that's the case, will this change? instead of q p star, will it be p star q? And what is the significance of this theorem? All that we shall discuss.